Hi, y'all. Ms. Blasky. Today is our last video for our review unit, Unit 0. We're going to talk about particulate representations. There's lots of different terms used for these representations. I call them either particulate representations or particle level diagrams are usually what I call them. But if we think about chemistry in a big, broader sense, there are multiple ways to describe the same thing that's happening. And one of the ways that we can sort of organize these different ways of representing the world around us is with this thing called Johnstone's triangle. You don't need to know who Johnstone is or was or will be, but this representation is something that we're going to be using a lot this year to help organize our thinking, to help us review, to help make sure that we really have a deep understanding of what's going on. So there are 3 different ways that we can represent chemical things. We can represent reactions, we can represent concepts, we can represent individual ideas. So there is the macroscopic, the microscopic, and the symbolic. So macroscopic, macro means big. So macroscopic explanations or definitions for things are what we can see with our eyes. So the examples given here are laboratory experiments or demonstrations. Symbolic is what we do a lot. This is writing out chemical or mathematical formulas. The sub-microscopic or the microscopic, because lots of times atoms are way smaller than a microscope can see, this is on the itty bitty little low. This is where we show what's actually happening to the particles, to the atoms, to the molecules in whatever situation is happening. Right? So some examples. If we wanted to talk about a particular chemical reaction, right? For our symbolic, we could say A plus B makes C. For our macroscopic, we could actually do that reaction. We could actually take a beaker of A and a beaker of B and mix them together and see what happens. This could be our observations. This could be, are there bubbles? Are there color changes? What's going on? What state of matter are they? All that sort of thing. But the sub-microscopic or the particle level is actually showing how do A and B come together to form C. And so that's really what we're going to talk about today. There are lots of different things that we can represent with these particle diagrams. So one of the things that we always need to consider when we're drawing particle level diagrams is what phase of matter something is. Because the way that those molecules are organized can tell us what phase of matter something is. If something is a solid, those particles are going to be nice and orderly arranged. They're going to be packed as close together as they can. They're not going to be moving a whole lot. We might see a little bit of jiggling, but not much. In a liquid, those particles are still going to be packed pretty close together, but we're not going to have that nice orderly pattern. They're going to be a little more jumbled up. In gases, we're going to have a lot of empty space between those particles, and we might even show some arrows to show the movement of those particles, because gas particles move a lot more than liquid and solid particles do. So that's one thing we can represent by showing these particles. Now notice, we represent these particles just with little circles. Sometimes I know in first year chemistry, you might have drawn squares or triangles or smiley faces or something else to represent that. We're just going to stick with circles. We can color code those circles. We can label those circles to show that there's different kinds of elements going on. Any of that is fine. We can show differences in elemental makeup. We can show the differences between elements, compounds, and mixtures in our drawings. So for example, this picture A, shows a 3-atom molecule. We can tell that there's three atoms because there's one big black circle and 2 little clear outlined circles, whatever you want to call them. This is probably representing water. We can see, since they're spread out, we know it's probably a gas. They're not all packed in together, even though there aren't arrows showing us what's going on. And we also know that this is a pure substance because there's only one type of molecule in that mixture or in that sample. Picture B, even without looking at the explanations down here, again, I can tell that it's a gas because those particles are spaced out. There's only one type of molecule in here. so that I know it is a pure substance. And this is a dimolecular or bimolecular molecule, two of the exact same atoms squished together. So this would be something like oxygen or hydrogen, any of those diatomics. And again, if I look down here, they're representing oxygen. Box C, now I see that there are two different types of particles in this box, so I know that this is now a mixture. I've got these water particles and these oxygen particles, still a gas because they're all floating around. D, same mixture, but a different ratio of particles. E, I know this is a solid. I can represent that by seeing how close those particles are together. Notice that some of them have positives and negatives on them, so this is probably ionic if I've got positive charges and negative charges. And it's a solid because everything is packed in, and I can see that there's space up here. They're not filling that space like a gas would. And then F, now we've got some of those ions are now separate from each other, and I got these water particles floating around. This represents a solution. Those ions have been dissolved in those water particles. So there's a lot of information that can come from these pictures. So not only do we need to be able to read the pictures to know what information is there, but we also need to be able to draw the pictures to share that information with others. The number of particles you represent can show as density or concentration. So if I have a 0.2 molar potassium chloride solution versus a 0.1 molar potassium chloride solution, there's going to be half as many particles. So I can represent that by how many particles are drawn in that diagram. I can also see whether something dissolves or doesn't dissolve. Magnesium chloride is going to be much more likely to be soluble in water, known as aqueous. Hydrofluoric acid, we will talk more about this later about why it doesn't dissolve, but it doesn't, so we can represent that as showing that hydrogen and that fluorine together versus the magnesium ions and the chloride ions being separate from each other. That shows us that it has dissolved. We can also represent chemical reactions. So here we have a reaction they tell us in the key that oxygens are these white circles, that hydrogen are the black circles. So I've got H2s and O2s reacting together. I know how these are going to react together. I know that two H2s are going to react with only one O2 to make two waters. Now notice that they've got these two oxygens over here that aren't in that circle. Why did they stay that way? Think about that for a second. Those would be oxygens that are limiting reactants. Those oxygens are just sort of hanging out. They're not changing, and so we still have to represent them as excess by being there, but they're not going to be changing as that reaction changes. So not only can we show what's happening in that reaction, but we can also show quantities. And even from this, we should be able to write out this equation. We should be able to represent what is limiting, what is excess. Even in terms of mathematics, we could maybe do some stoichiometry with that there, right? So when you are drawing out your particle diagrams, things to think about. You need to think about the ratio of reactants and products if you're drawing it out for a balanced equation. You need to think about conservation of mass. How many particles are there? You can't just make particles disappear. And remember that it's possible to have those limiting reactants. Okay. So I want to take a look at example number 44 because we've got some choices here. So we've got a diagram here. It's usually good to label things somehow or to see if there's a specific way you're supposed to identify your particles in the problem. So here they tell us that the dark spots are hydrogen and the white spots are oxygen. We know that it's in a sealed container. Which of the following pictures would be the best representation of the products if the reaction below were to run to completion? So that means the reaction is going to proceed as far as it can. From our balanced equation, we can see that two hydrogen molecules react with one oxygen molecule. So if we look at our equation here, two hydrogens are going to react with one oxygen. So just from those circled particles, I'm going to get two water molecules. See how we have conservation of mass? There's 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens, and then 2 oxygens, 2 oxygens. And then we've got this O2 left over that must be acting as excess. It's not changing in the reaction, it's excess, it has nothing to react with, so it's just gonna hang out by itself. So if we look at our choices, A is out because it shows those oxygens being separate from each other. There's nothing in our reaction that tells us that those oxygens are going to split up into atoms instead of being in a molecule. So A is out. B, we've got, that's not even a water molecule. That's 2 oxygens and a hydrogen. So that's out. C, again, that's 2 oxygens and a hydrogen. That's out. D, D looks promising. There's the 2 water molecules that we made, plus that excess oxygen. And then E shows the 2 water molecules, but it doesn't show the excess oxygen, so that one is out. The answer would have to be D. Drawing out these particle diagrams is something that we are going to do for every unit we do. And we're actually going to use that Johnstone's triangle to review, to check our work, to see if we really understand what's going on at all 3 levels of representation, macroscopic, microscopic, and mathematical. If you've got questions about this, let me know. We're going to be doing some work in class on this. We're going to continue it all throughout the year. But this is our last topic for our review unit. Next up, we move on to new stuff. As always, if you got questions, let me know. Otherwise, I'll see you later.